Just a little teardown of an electronic fluorescence tube starter. Let's zoom down a little bit. And I have that paper to doodle how the circuit of some fluorescence tube lighting actually looks like, so we know where that thing comes in. But you see the markings here, it's in German. Schnellstarter. Schnellstarter means a fast starter. It's an electronic starter with type number 553119, and it has the probably China export mark. Yeah, I got it on a trade fair, and it's good for fluorescence tubes from 4 to 125 watts. And yeah, it's for our European 220 to 240 volts and 50 to 60 hertz. And that thing is sold, still sold, on Amazon, for example, here in Europe. And that specific piece here didn't last even a year in operation in the kitchen. So yeah, let's say 2 to 4, at max 5 power cycles a year. And yeah, best guess, it gave up after half a year or so. As I said, a year at most, you do the math. So stay away from these. You get brand named Osram and such fluorescence tube starters for less than $1. So yeah, where do you need that thing actually in all that circuitry with a fluorescence tube? And that has been probably explained on YouTube 1,000 times, so I keep it short. Here is our fluorescence tube, and the problem with these thingies is it needs an ignition voltage of 400 or greater than 400 volts. Once it ignited, it can operate, depending on the tube type, the gas filling, etc., length, between 50 volts and 110 volts. So how do we get that thing to ignite? Or assuming it did already ignite, how can we keep that thing from blowing up when connected to mains AC, which is, in part of the world, 220, 230, 240 volts. In other parts of the world, 110, 120 volts. But in these parts, your tubes probably operate more around in the 50 volt range. But so we have a big ass inductivity here in line with the tube and the mains AC to, during normal operation, limit the current or the voltage across the tube. So far so good. We still haven't ignited the tube. And there comes in the starter. Exactly. So the classic starter basically consists of a little neon lamp and a bimetal temperature switch. Of course, thermically coupled. So the switch is normally open, and if it heats up, it will close the circuit. So what happens if we flip the light switch and put mains AC here? We said, okay, this cannot ignite, so that little neon lamp will light up and heat up the switch. And important design feature here, that neon lamp should be operating only in a voltage that is greater, the 50 to 110 volts, than the voltage across our fluorescence lamp should be into normal operation. That's important design feature. we'll come back to that. Anyway, things are heating up and that switch is closing. Now, two things happen. First, we got a closed circuit here. Yeah, so we have suddenly some current through our big ass inductivity. And yeah, these are actually little filaments here at the end. So there are sometimes these are also called hot cathode tubes. But yeah, since we're running them with AC, you cannot really say what's anode and what's cathode. It's yeah, the same. So little filaments here, heating filaments, and you can see that in the dark when you switch on some fluorescence tubes. Yeah, they light up and they provide a little bit of ionization here at the end. The problem is we have closed that switch here now. Yeah, remember? So basically we shorted out our neon lamp. So the whole thing is cooling down again, and at some point it will inevitably open. And what we have then is, hopefully, an inductivity which has a lot of current flowing through it. Yeah, when you're just mains AC, yeah, let's say we were here somewhere at the peak of the AC when our switch opened again. So we have a lot of current going through there, and suddenly, yeah, we open the switch. And what does a inductivity does when it has current through it, and suddenly you have a whole lot of resistance, yeah, that little neon lamp plus this little lamp, it generates a high voltage spike. So on top of the mains AC, we have the voltage spike generated by that inductivity now going, yeah, through our fluorescence tube and igniting it normally. Of course, you can have bad luck and the switch opens when the current through our inductivity is at zero. Then simply nothing will happen and the whole cycle repeats again. But anyway, let's see, and it could do that 1, 2, 3 times, and yeah, by the laws of probabilities, somewhere at some point you open the switch at a good point where there is current going through the inductivity. Where was I? Yeah, exactly. Okay, now the current, yeah, we have ignition. The current is going through our fluorescence tube. We have full ionization through here, and so the operation voltage, yeah, across it drops down to 50 to 110 volts, yeah, depending on the type and where you live. And our current is limited by that big inductivity. And of course, our little neon lamp here, yeah, we said, okay, that it has operation voltage greater than 50 to 110 volts. That's no longer lighting up and no longer heating the bimetal switch. So it stays open and voila, you've got light. And now let's turn that thing here apart and look what's inside. Yeah, and I cannot really bothered to try a non-destructive approach here, so let's cut that open. Time. Okay. That's interesting. I need to zoom down a little bit more. Okay, interestingly, we have a temperature switch here. Is that a temperature switch? I will look it up, but I think so. some resistors, a diode, some capacitors, nothing on the back, and this basically looks like another capacitor. I don't see any markings. I guess it's a capacitor. Yeah, it's definitely a capacitor. So yeah, the relay, interestingly, has also no markings. And these are second or something. Okay, reverse engineer. Just a second. So I reverse engineered that thing, the usual, taking a picture of the back, mirroring the image, and yeah, picture of the front, redundant because I still had this to look at, and I came up with that circuit. And that's exactly the circuit that is given in the German Wikipedia. I will put a link down below in the description for an outdated half electronic, because this is a relay. Yeah, we have that relay on board for an outdated half electronic starter. So again, stay away from these thingies. And yeah, interestingly, that circuit is not given in the English Wikipedia. So, and I haven't found it anywhere else Googling around. So, yeah, so how does that work? Yeah, remember, here's our starter, and I forgot something here. Just to keep switching noise down, there's normally an X-type capacitor across here. Yeah, not much, a few nanofarads. Okay, just yeah, when the switch actuates, yeah, to keep the noise down. So, and we placed that with that. So what's happening here? Yeah, if you have are in a negative half wave, when you switch on your lamp, nothing happens. So this is our relay. This is our normally closed here position. And you see if here is negative and here is positive, yeah, nothing happens. This basically does nothing, this part. It's yeah, isolated by the relay. And that diode, that's a 1N4007, like that one here, yeah, it blocks anything coming through. So it gets interesting when we are going into the positive wave here. And now it depends. If your lamp here is already ignited and operating, you know, voltage across here is then, yeah, about 50 to 110 volts. So we would plateau up somewhere here. Again, nothing happens because that MOF here is blocking up to, yeah, the operation voltage of your lamp. Okay, so that simply blocks. If the lamp is not already on, ignited, then the voltage rises. Yeah, the MOF becomes conductive and charges via that 1K resistor this capacitor. And this is, yeah, you can see it, this is the 47 microfarad capacitor, and if I need to guess, just 16 volts. Yeah, this is probably a 12 volt, might be a 6 volt relay, I don't know, something like that, maybe 24 volts. Then this is probably, yeah, but then this cap is too small for 50 volt 47 microfarad, far too small. So probably just 16 volt, something small. Where was I? Yeah, we're charging up here, and I did some, with these values, some back of the envelope calculations. So we have about, the relay coil is 380 ohms of that really small relay here. And we have, order of magnitude, 10th of milliamps consumed here in parallel when this is charged up, but we are charging here with 100, 200 milliamps. And so after a few milliseconds, when we're here in the positive half wave, the relay switches. And what happens then? We're still in the positive half wave. That diode here, it's also, do I have green? Yeah, I told you. It's a 1N4007. That diode does nothing. Yeah, it's blocking. We open the switch in a very controlled manner, like that switch would open when it gets heated up. And we get, of course, doodle, running out of paper up here. And we get that nice inductive spike. Yeah. From our inductivity here to ignite our lamp. That's all. And yeah, this will fall down at some point. And the relay, of course, this also discharges, the capacitor is discharged by the relay also in a few milliseconds. So this will switch back in, its normal open position. And when the lamp has ignited for the next cycle, next positive cycle, nothing will happen because the MOF blocks everything. Now what's that about here? This RC element. My best guess is that this is just here to, I have to align my papers, to a quenching circuit, basically, to limit that voltage spike here, I mean, we need something greater, 400 volts, here, but we probably don't want to have 1,000 volts, a really high spike. So this is keeping things a little bit down. And this, did I mention that one? This is also just analog to the old, it's not really analog to the neon lamp and bimetal switch thingy, just another noise suppression. And that's it. That's how I imagine this works. And timing is in this circuit is really critical. So at 50 hertz, one of your half waves is just 10 milliseconds. So within a few milliseconds, when we're basically at the crest here, this relay opens and it hopefully has closed again, the capacitor discharged by the time we go into a negative half wave. Because when we are in a negative half wave, and we would still here have connected the green circuit through the relay, yeah, we would go right through the diode and basically short out our lamp here, yeah, for a negative half wave, and basically kill it, and then we would have to ignite it again. Now, even Wikipedia was very wary about that circuit, and I'm too. First of all, this little poor relay here has to handle some very harsh voltage spikes just as it's opening. So you probably have a lot of arcing in here. Maybe it's even the relay that died, because everything else looks just fine. So yeah, no bulging here, nothing blowing up. Yeah, and 100 milliamps going through that 1K resistor is also yeah, a bit much, or maybe 200, 300 at times at peaks, but it's only for a few milliseconds. So yeah, these resistors here and that resistor, quarter watt, more eighth of a watt or so, they'll survive. They survive. And that fuse here, yeah, it's a temperature fuse, very conservatively set for 85 degrees C. So yeah, but still a great example for value engineering, and not something that will survive for very long. The old conventional starter with yeah, neon lamp, bimetal, it lasted for a decade or so, and this for, yeah, half a year, max a year. That's it. Bye.